Welcome to Chapter 5, where we explore X-ray photoelectron spectroscopy, commonly known as XPS. This powerful surface analysis technique probes the elemental composition and chemical states of materials at the atomic level. By irradiating a sample with X-rays and measuring the kinetic energy of ejected electrons, we can determine binding energies that reveal both what elements are present and their chemical environment. XPS is indispensable in materials science, catalysis research, and thin film characterization. XPS is based on the photoelectric effect, explained by Einstein in 1905. When an X-ray photon with energy hν strikes a material, it can eject a core electron if the photon energy exceeds the electron's binding energy plus the work function. The fundamental equation is binding energy equals photon energy minus kinetic energy minus the work function. The binding energy is characteristic of each element and its chemical state. By measuring the kinetic energy of ejected electrons, we can determine binding energies and thus identify elements and their bonding environment. An XPS instrument requires several key components operating under ultra-high vacuum. The X-ray source typically uses aluminum or magnesium anodes, producing characteristic X-rays at 1486.6 eV or 1253.6 eV, respectively. The sample chamber must maintain pressures below 10 to the -9 millibar, mainly to keep the surface free of adsorbed contamination during the measurement, and also so photoelectrons reach the analyzer without being scattered by residual gas. Ejected photoelectrons travel through a hemispherical energy analyzer that separates them by kinetic energy before reaching the detector. Charge neutralizers compensate for sample charging in insulating materials. Survey spectra provide a broad overview of elemental composition by scanning across a wide binding energy range. Typically 0 to 1200 eV characteristic peaks appear at specific binding energies. Carbon ones near 285 eV, oxygen ones near 530 eV, and various core levels for other elements. Auger peaks also appear, but are identified separately. While survey scans offer lower resolution, they enable rapid element identification and semi-quantitative composition analysis. Peak areas, after correction for sensitivity factors, provide atomic percentages. High-resolution XPS scans focus on specific elemental regions to reveal chemical state information. The carbon 1's region is a perfect example. Carbon bonded only to carbon and hydrogen appears at 284.8 eV, while oxygen-bonded carbons shift to higher binding energies. Carbon singly bonded to oxygen appears around 286.2 eV, carbonyl carbon near 287.8 eV, and carboxyl or ester carbon around 289 eV. Peak fitting deconvolutes these overlapping components, providing quantitative information about functional groups present in the sample. Chemical shifts in XPS directly correlate with oxidation states. As electrons are withdrawn from an atom through bonding to electronegative elements or oxidation, the remaining core electrons experience increased nuclear attraction, raising their binding energy. The iron 2p spectrum beautifully illustrates this. Metallic iron's 2p3/2 peak appears at 707 eV, while iron 3 plus oxide shifts to 711 eV. The general rule is that higher oxidation states produce higher binding energies. This makes XPS invaluable for studying corrosion, catalysis, and surface chemistry. Accurate XPS analysis requires proper peak fitting using Voigt functions. The Voigt profile is a convolution of Gaussian and Lorentzian components. The Gaussian contribution arises from instrumental broadening and surface heterogeneity, while the Lorentzian component reflects the natural lifetime broadening of the core hole state. Key fitting parameters include peak position, full width at half maximum, integrated area, and the Gaussian-Lorentzian ratio. Residual plots below the fit help assess fitting quality. Proper background subtraction using Shirley or Taugard methods is essential. Quantitative XBS analysis converts peak areas to atomic concentrations using relative sensitivity factors. The quantification equation divides each peak area by its sensitivity factor, then normalizes by the sum of all corrected areas. Sensitivity factors vary by element due to differences in photoionization cross-sections and analyzer transmission. On the widely used Wagner scale, fluorine 1s is set to 1, with carbon 1s at 0.25, oxygen 1s at 0.66, and iron 2p at 2.96. These factors depend on the specific instrument and X-ray source, so using manufacturer-provided values is important. A systematic workflow ensures reliable XBS analysis. Start with a survey scan for element identification. Acquire high-resolution spectra of relevant regions. Apply charge correction by referencing adventitious carbon to 284.8 EV, subtract appropriate backgrounds using Shirley or Taugard methods. Fit peaks using constrained Voigt functions with chemically reasonable parameters. Finally, quantify using sensitivity factors. Decision points include checking for sample charging and evaluating fit quality through residuals. This systematic approach produces reproducible, publication-quality results. Let's review the essential XBS concepts. The photoelectric effect provides the foundation, with binding energy equaling photon energy minus kinetic energy minus work function. XBS is inherently surface-sensitive, probing only the top 1 to 10 nanometers. Chemical shifts in binding energy reveal oxidation states and bonding environment. Voigt functions enable accurate peak fitting by combining Gaussian and Lorentzian contributions. Sensitivity factors convert peak areas to atomic concentrations. In Chapter 6, we'll apply Python programming to automate spectroscopic data analysis. Practice by analyzing an XBS survey spectrum to identify elements.